Hi everyone, I'm Anish and welcome to PrepFusion. So today we'll be starting the lecture 5 of this root locus chapter, right? So in the previous lecture we completed the basics of root locus, basically all the steps we did with relevant examples, right? So here I will try to solve questions in faster manner so that in exam how you solve, right, that approach you should develop also, right? So in exam you should solve in faster manner. So here you are clearing your concepts, so building up your concepts, so you will solve it slower. Okay, after now in this session you will pause the video and you try to solve it faster, right? So obviously, right, to solve it faster you don't have to find all the values, right? So basically you don't have to find the break-in point, the breakaway point, the angle of asymptotes. Like angle of asymptotes you find, that is very fast to calculate, but the angle of arrival, angle of departure, that you don't need to find. With intuition also you can find that, right? I mean, with intuition also you can get a basic approximation what my root locus will look like, right? So yeah, that we will do, right? So these are the two questions. First, these are the two questions. We'll do more questions. So take the screenshot, right, and plot the root locus for these two. So now I will start. Okay, so first what I see is, let me copy this OLTF. So if I copy this OLTF, right, what do I see? That what are my number of poles? Number of poles is 2, number of zeros is 2 also. So number of branches will be 2. Okay, and number of virtual zeros or asymptotes will be none. Okay, so Z virtual will be none. Okay, so one calculation is already gone, the asymptote calculation is already gone. So can I find the poles and zeros? So the zeros poles are easy to find. They are at -1 and -3. So SP is at -1 and -3, and this is a step 1 basically what I am doing. Okay, so what is SZ? So this is a very famous equation. Basically this is like that equation, right? 1 plus j square plus 1, like that equation, which is basically equals to, the roots of this one is -half plus minus √3/2, j √3/2, right? So if you do, like, apply the Sridhara Acharya formula, what you see is -1 plus minus b square 1 minus 4. Okay, that becomes under root -3/2. So yeah, basically you get 1/2 plus minus j √3/2. Okay, so this is what are my zeros are. So yeah, so let me plot along with this, right? So if I plot along with this, so everything is on the left hand side. So this is j omega and this is -1. Okay, I will write the -1 a bit here. -1, -3, and like these are at -half and √3/2, right? √3/2. Okay, so yeah, these are here only, right? Sorry, these are zeros. Sorry, these are not poles. Okay, that going too fast, right? Going too fast. So these are poles. Okay, I'm just drawing a rough drawing. Okay, so now what is happening? What I can say, next step is identifying the real axis, right? I mean, identifying the test point where it lies in the real axis. So what I can see is here, right, I have odd number of poles and zeros, and here I have even. So here it can't lie. So in this range it will lie, right? Okay, so I'm going it fast, so you have to understand, right? So now you have to understand. So this is -3. So S test will lie between -3 and -1. So I will lie between here, right? And I will have two branches. Okay, I will have two branches. They will be something like this. And what is happening, basically from poles it is starting, right? So from poles it will start and then it will break away. Now can this break away here? If this break away here, that means I have asymptotes here, which is not possible, right? I don't have any asymptotes. So this has to go here and terminate on the zeros only. So this will go like here only, right? So from basic intuition understanding also you can understand that my root locus will look something like this. Okay, root locus will look something like this. So yeah, by this basic understanding also you can see these are zeros. Basically I should write them as zeros. This is -1/2 plus j √3/2, and this is -1/2 minus j √3/2. Okay, yeah, these are basically what my zeros look like, right? These are my zeros basically. So this is my root locus. So it will never, like from here I can say it will never cut my j omega axis. Here I can say the break away point will be somewhere between -3 and -1, and yeah, all these are good, right? So yeah, now if you want to calculate, now your question is done. If they has already like given 4 options and you have to find the root locus, you can directly find it from here. But now if there are similar root locus present in the options, you have to go further. You have to find the breakaway points, right? Then you have to find the value of k for which different values of k, okay, at this breakaway point. So for which the system is underdamped, overdamped, critical damped, all those things you have to find out, right? So yeah, let's first find the breakaway point basically. So this is the step 4 basically, because step 3 is asymptotes and asymptote isn't present over here. So what is my breakaway point again, right? What is my OLTF? OLTF is this one, okay? So from here, what is A of s? A of s is s square s plus 1, okay? And what is B of s? B of s is s plus 1 into s plus 3. Okay, so I will write this in polynomial form. So this is basically s square plus 4s plus 3, right? So this is in polynomial form. So now simply to find the break away point, right? So the same Kisa Pita formula we write, that is a dash of s into b of s minus a of s into b dash of s should be equal to 0, right? Should be equal to 0. So if it should be equal to 0, then you just write it down. So you can do that dk by ds equals to 0 also. That also you can do, right? So that comes to the same conclusion, right? I'm directly writing the conclusion. So a dash of s is 2s plus 1 into b of s, which is s square plus 4s plus 3 minus a of s. A of s is s square plus s plus 1 now into b dash of s, which is 2s plus 4, okay? So yeah, this is this one. So now this is equals to 0. So what is like the final equation? So this is 2s cube plus 8a square plus 8a square and plus 6s plus s square plus 4s plus 3 and this is minus, this is basically s cube, 2s cube basically, then this is basically 4s square, then this is basically 2s square, then this is plus 4s and this is 2s plus 4, 2s plus 4, okay, which is equals to 0, okay? So this is this one. So now let's get the final expression basically. So this 2s cube gets cancelled, so we have 8s square here, and this is also another s square, so this is 9s square, okay? I'm like getting the like terms together, and this is 10s and this is plus 3, okay? And this is minus 2s square and 4s square, which is 6s square plus 6s plus 4 equals to 0, right? Equals to 0. So now simply we have to subtract this one. So if I subtract this one, what do I get? I get 3s square plus 4s minus 1 equals to 0. So again use a Sridharacharya formula. So we can see minus 4 plus minus b square 16 minus 4ac. So this will be plus because 4ac I'm adding, right? So b square just 12, right? Just 12, okay? this is divided by 6 basically, divided by 6. So this under root 28 basically. So what is under root 28? So okay, I haven't actually calculated it, I have to calculate it, so I will calculate and then write it down directly. So what is under root 28? Okay, this one I have written down. Generally I do write things down. So 28 under root is 5.29, right? 5.29 divided by 6 basically. So what do I get my final answer as? So like I will get two answers, right? So first I will write this minus 4 divided by 6. This is basically 0.215, and okay, I will take this one to the next page actually. And what is the next answer? And this is minus 5.29 4 minus 5.29 divided by 6. So this is almost equals to minus 1.548, right? Okay, not equals to, these are the two solutions, right? Two solutions I am getting. So tell me which one is valid and which one isn't valid, right? So what was my range, right? I have written my range of in the real axis. Okay, the range is between minus 3 to minus 1. Range is between minus 3 to minus 1, right? So what I can understand from here is that obviously this is invalid, right? This is invalid and this is valid, right? This is valid. Okay, so yeah, that is what the answer is. So my breakaway point will be this one, because obviously I can't have a breakaway point here, right? Because this invalid, this will not lie in the root locus, that we already established, right? So yeah, that is basically it. Now what is the value of k for that breakaway point, right? So let's find the value of k. Again, right, I don't have like calculated this one, so sorry, apologies. So I have to calculate it here only. So what was like 1 plus g of s? It was this, right? So 1 plus g of s is this, so this will go above and this will go in the bottom, right? So this is basically minus, you can do it like very fast, right? Okay, now I'm doing it very fast because in first cases I have solved it very slowly. Okay, so if you're not understanding, obviously you have to revise, right? Revise. So s square plus s, okay, plus 1. Okay, so now I'm putting the value of s equals to minus 1.55, I can put approximately. So 1.55 whole square plus 4 times 1.55 basically. Okay, this is a bit wrong. Then plus 3, this is almost equals to minus 0.597, right? Okay, now 1.55 whole square plus 1, okay, minus 1.55 basically, and plus 1 again. So I get 1.8525, and I have a minus sign here also. Okay, so what do I get? I get this into 0.597 and like minus n is gone, so this is almost 0.32. okay, almost 0.32. so value of k will be almost 0.32, right? So this is my value of k breakaway point. Okay, and write this in color. And so this is my s breakaway point, right? S breakaway point. So yeah, these are the 2 points. These needs basically bit of time. Now let's calculate the angle of arrival, right? So I told you, right, in previous lecture that we will calculate more angle of arrivals, and there we'll understand the concept bit better, right? So yeah, let's calculate the angle of arrival this time, because I don't have angle of departure, because I have only open loop complex zeros and not poles, right? So this is the important step. So let's find the angle of arrival. right? So I will first, what I will do is I will basically draw the sigma of j omega axis. Sigma j omega axis, right? So I have two open loop zeros, one is here and another is here, two open loop complex zeros, right? Complex conjugate zeros, and I have two open loop poles, one is around here and one is around here, right? This is -1 and this is -3. And -12 j root 3 by 2, and this is minus, right? This is minus, this is plus j root 3 by 2, right? So this is my -12 one. Now I have to find the angle of arrival. Okay, so one thing I know, it will arrive something like this, so I can like draw it, or I'm not drawing it. So what I will do is I have to find the angle with respect to this one, right? This one I have to find the angle. So this is like, let's name this pole as theta p2. So this will be my theta p2, and let's name this one as theta p1. So this will be my theta p1. Okay, so this will be my theta p1 and this will be my theta p2, right? And let's, with respect to this 0, right, name this as theta z basically. Now what was the angle of z, what was the angle of arrival? Angle of arrival was for what? Angle of arrival was for open loop zeros, right? So if it is for 0, then remember how I told you to remember the formula, right? Basically angle of arrival will be equals to 180 plus the summation of poles. Poles won't get subtracted, but the zeros will, right? Zeros will, because I am calculating for zeros. Okay, that's how you remember it. So because obviously you don't want to derive, right? You don't want to derive, obviously you just want to write the formula and get to the answer, right? So in the gate, obviously you have to get to the answer. So for this question, let's say if they would have asked to find the angle of arrival, like this you calculate, right? So like this you calculate. So this will be theta a equals to 180 plus theta z. Now what is this theta p? So I have two poles, right? Theta p will be basically theta p1 plus theta p2. Okay, summation of theta p1 plus theta p2. So before starting this, right, what is my theta p1, right? So what is my theta p1? So again, right, I will write it in terms of x and y. From there you will understand, right? So I want to go to this point. So what I know is I have to move my head a bit above, but not totally, right? Totally, I have to go ahead also and a bit up, right? So this is somewhere between 0 to 90. Let's see if my hypothesis is true or not. So here, right, what is the distance between these 2 points? Like what is the x coordinate distance? So the x coordinate distance, right, if I can choose a different color, yeah, here. So x coordinate distance I can see is the half, right? X coordinate distance is half. Okay, so x coordinate distance is half. What is the y coordinate distance between these 2 points, right? So y coordinate distance between these 2 points is root 3 by 2. So y coordinate distance between these 2 points is root 3 by 2, right? So x and y I know. Now I can find the simple angle, and this is, both of them are positive with respect to this, right? With respect to this, I have to go ahead and up. Okay, so in the first quadrant I'm lying, so this is positive theta. So theta p1 will be simply tan inverse root 3 by 2 divided by 1 by 2 y by x, right? So it is tan inverse root 3, which is simply equals to 60 itself, right? Which is simply equals to 60 itself. That we know. Now what is theta p2? What is theta p2? So what is the x distance? Y distance is same, right? Both of them are lying on the real axis, so the y height will be same, that is root 3 by 2, but x has increased further by 2 units, because here already I had half and further 2 units I'm going behind, so this will be further 2 units. Okay, so again this is positive, right? So it is in front of 3 minus 3 and above minus 3, so it is again in the first quadrant, right? This point, this 0 is again in the first quadrant, so again my angle will be tan inverse y upon x simply, right? So tan inverse where is tan inverse? Sorry if some sound is coming from outside, some festival is going on, I don't know. So tan inverse y upon x, y is this time again same, right? Root 3 by 2, and x is simply 2 plus half, which is 5 by 2. Okay, so it is tan inverse root 3 by 5, right? Is tan inverse root 3 by 5. Now what is tan inverse root 3 by 5? Let's find it out. So I have already written it down, but still I want to recalculate. So it is root 3 divided by 5, and we have to do tan inverse of that. So it is almost 19 degrees, right? It is almost 19 degrees. So theta p2, right? So I'll take this to the next page. Basically tan inverse, this will be almost 19 degrees. Okay, so I will take this onto the next page. So what will, now I have to find the angle of, okay, angle of what do you say, 0 also, right? But that is very easy. Why? Because what will my theta z? Theta z is simply basically my x, right? X is 0, okay, because it is just above my head. Okay, exactly above my head. So x is 0, but y is finite, which is basically root 3, right? Which is root 3. So but it doesn't matter, because root 3 by 0 is tan inverse infinity, which is 90 itself. Okay, tan inverse infinity is 90 itself. So you get theta z as 90. Now what is my angle? So angle will be, I will put all of this into formulas. So this will be simply 60 plus 19 minus 90, right? Theta z is getting subtracted. So this is basically almost 80, and this is like a minus 20, minus 90. So 80 and minus 10, minus 10 and minus 70, and still we have to add subtract one more. So this will be 169 degrees, right? So this will be 169 degrees almost. Okay, so yeah, I hope you understood the concept basically. That how do I calculate the angle? So I've calculated this bit fast to show you that you can calculate it much faster than this, right? So minus this 169 will be my angle of arrival, right, of the zeros. Okay, so now let's find whether they will cross over or not. But from here, from the diagram itself, I can understand they will not cross over. Okay, so the sixth step, basically no crossover point. From intuition itself I can understand, right? I don't need to solve further. So the like the root locus that we get, right? Root locus that we get is this one. Okay, root locus that we get is this one. This one I have already brought up with MATLAB. I haven't drawn it. Okay, this will take time. So yeah. So but what are the few regions basically? What are the few regions? So the few regions are basically here, right? So at this point, if I can write here, if I may write here, at this point, what is the value of k? This is a breakaway point, right? The value of k was 0.32, right? 0.32. Here I have critically damped system. So this is k equals to 0.32. This is k equals to infinity. Okay, and this is also k equals to infinity. K equal to 0. Okay, so sorry, yeah, this is k equal to 0, right? This is also k equal to 0. So k is starting from 0 and it is going like this one, and I can write the ranges, right? I can simply write the ranges. So what are my ranges? So like for like what is the breakaway point basically here is breakaway point equals to, what was it? I forgot actually. Oh no. Oh no, everything got messed up. Yeah, now it's fine. So breakaway point was basically to what location? Okay, angle of arrival I have to also write. It was at 1.55, right? 1.55 minus 1.55. 5 and what is the angle, right? The angle from the angle of arrival from the x-axis is 169 degrees, right? And the opposite one will be simply minus 169. Okay, I can't simply move this one, that is difficult. Simply moving this one is difficult, so okay, everything got messed up, sorry. Okay, this is difficult, but still now it's fine. Okay, basically this angle, right? This angle will be minus 169 that I am not writing. So let's go to the second one. Okay, the second one is even more faster, and what will be the homework for you is find the break in or breakaway point and the angle of arrival or departure. Whatever is present, you find that, right? You will see that you are getting almost the same answer, okay, as the previous case, right? Just a few things have swapped and one answer will be different. What will be different, do let me know in the comment. Okay, everything will be almost same except the zeros and poles, everything will be almost same. Okay, but one parameter will differ in values, right? Okay, but the angle of here, right, what we have, instead of angle of arrival we will have angle of departure, that value will be same. Okay, and the break away point will also be same. Instead of break away point, this time I will have break in points, because this time, right, I will have two zeros, right, two zeros, real zeros. So let me copy the characteristics equation, there you will understand. So these are my two real zeros, right, basically. So these are my two real zeros. So if these are my two real zeros, what do I see? Basically, like there will be breaking point, the breaking point and the breakaway point will be same, like previous example, whatever the breakaway point value was, and here it will same. But what will differ? Tell me what will differ. Okay, only one parameter I haven't talked about, so that will differ. So let me know in the comments. So here, right, again doing the same thing. Step 1 is basically find the poles. So poles, right, poles will be again minus 1 plus minus j root 3 by 2, right, and zeros, right, zeros equals to minus 1 and minus 3. So branches, like again will be 2 only, this same only, just the numerator and denominator have been swapped, right, swapped. So this is what my branches are. Okay, and like I don't have any asymptotes. Okay, so that is gone. Breakaway point and breaking point is homework for you, so that you will find, and the angle of departure or arrival, that you will find. Okay, so obviously there is departure, no arrival, because roots are on this plane. So this is this one. So it will look something absolutely similar to the basically previous example, right? So I will do this in full manner. Okay, so yeah, this we will do, and this is basically minus of only, and find this point, right, find this point and the value of k here, and find the angle of departure. Basically this is the angle of departure, right, find theta d. Okay, find s break in point, right, break in between two adjacent zero, we have break in point. So these are homework for you. So I directly did it. Okay, but I didn't even look at this because like I didn't do the explanation, because here, right, it will lie on the real axis because I have odd number of zeros here. Okay, so didn't do the explanation, but like we have done so many questions now, so this should be in your tip of tongue, or like just by seconds you should solve this, right? So this will be my s in the real axis will lie between minus 3 and minus 1. Okay, so yeah, this way you can solve. I will not find the breakaway and breaking points this time, right? I will not find the breakaway and breaking points. Okay, so what what you will observe is you got this value of k, right? where was it? You got this value of k. So if you take the inverse of this, you will get that same value, or you will not. So yeah, I have to think that through. So I will think that through, and then I will tell you the answer. Okay, so yeah, I will do this, and then I will solve this, and then like in the notes you can see the solution. Okay, so yeah, let's now do the basically what do you say, let's now do the next question, which is the okay, this is the graph that we will get, right? This is the graph that we will get. Okay, for this one, same graph only, just the zeros and poles have been interchanged. Basically zeros and poles have been interchanged. Okay, so let's do this question now. So what is this question telling us? So we have to plot the root of Locus diagram for the following characteristics equation. Okay, for the following characteristics equation. So this is the equation. Now what is the system parameter? It is this, right? So in this question, right, first what you have to do is you try to solve it by yourself, but now I will tell. First what you have to do is basically like make this k alone, right? Make this k alone and all the other terms alone. Okay, so that my k is on that standard format that I used to know, standard OLTF format, right? That k into s plus z1 z2, and in the denominator we have s plus p1 p2, or like that, right? So I want to convert this into standard form. So what I have to do is convert this. So the question may not come directly blatantly, so maybe sometimes they may come a bit twisted like this, right? So convert this into standard form, right? So if I convert this into standard form, what do I get? So this is s square. So I will take all the other terms which are not present with k in one side, and the k will be separated. So s square plus 2s plus 2 is this one, and now the k terms I will take it together. So this is sk minus 4k equals to 0. So this is how my equation will look like. So now what I'll do, I will take common this k. Okay, this will be s square plus 2s plus k into s minus 2, s minus 4, basically s minus 4, right? And this is equal to 0. So now from here I will divide by this one. So now I will get my standard format, which is 1 plus g of s h of s, right? That format, right? So I will divide this by this one. So this will be k into s minus 4 divided by s square plus 2s plus 2 equals to 0. Okay, so this will be my standard format, right? So from here I can write my OLTF g of s into h of s equals to k into s minus 4 divided by s square plus 2s plus 2. Okay, so this is my standard format. Now what you should do is basically now vary the system parameter k. So always when you are given some non-standard format, you try to convert this into standard format, and then you start your steps for the root locus diagram, right? Whatever steps we have done. So again, right, what are the root? So first will be finding the open loop zeros and open loop poles, right? So open loop zeros is easy only, right? So open loop 0 sz equals to 4, sz equals to 4, and what are my open loop zeros? So for that I have to again apply the Sridhar Acharya formula. So this is minus 2 plus minus b square minus 4ac. This one will come out to basically minus plus minus j, right? So this is a very standard equation also. So minus 1 plus minus j. Okay, so yeah, this is this one. So like here, right, I have two number of poles, number of zeros are 2. So how many branches I will have? Branches again, right, I will have 2. Okay, but there will be some difference this time. Okay, so let's see what will the difference be. So again, right, so I will draw this and I will do the step 2 simultaneously. Okay, sorry, my zeros are only 1, number of zeros are only 1, so I will have an asymptote this time. I like भावना पे बह गया था, तो हाँ, I will have asymptote this time, and this is sigma and this is g omega. So like if I have only one asymptote, right, this will lie on the 180 degree axis, that we already know. So I can do step 2 and step 3 with one step only. Okay, so I will have one asymptote, and like the poles will lie around here. This will be one of the poles and this will be one of the poles, which is equals to minus 1, and this is equals to plus minus j1. Plus minus, right? So yeah, this is minus 1, and now where is the 0? 0 is at, okay, sorry, the 0 is at right hand side, right? 0 is at s equals to 4, so 0 is at the right hand side, so I have to move everything, so this is difficult. Okay, sorry for not being, okay, 0 is at the right hand side. Okay, move everything. So here, okay, this is my sigma naught 0. 0 is here around 4, right? So obviously this will lie around here, because like we'll understand the reasons. Because let's say if this isn't here, right, this isn't here, so again, right, that real axis rule, what it has to follow is that at my right hand side I should have odd number of poles and zeros. So here I have always have 1 0, right? If I go here, I don't have any pole or zero, none, right? That is even. Here I have always 1 pole and 0, so this will go on this whole real axis, so I will lie in the whole real axis, right? So my asymptote will go here, right, because I have another branch going to that side, right? So yeah, basically S test will be minus infinity to minus, not minus 4, right, this time 4. Okay, so S test will lie between these 2 points. Okay, so now what is my theta asymptote? So if we have already done this, that is 180, but still, just for the sake of it, so what is my theta asymptote? Theta asymptote is basically 180 where p minus z, which is 1. Okay, p minus z is 1 because I have 2 poles and 1 0, which is equals to 180 itself, right? 180. Okay, so yeah, this is this one. So like I'm going very fast. Okay, so you have to go fast like this if you are in exam. Okay, so now like what is the centroid? As asymptote is lying in the real axis, so there is no concept of centroid. So I write this one. There is no concept of centroid. Okay, so there is no concept of centroid. So yeah, that is that one. Now what are my break in and breakaway points? So like you try to find it out. Okay, so they will be in between 2 zeros. Okay, so finding the break in and breakaway point is homework for you. So few things are homework for you. I will write this down after this lecture finishes. Okay, so or like what will happen, you will get the notes at the starting itself, so you may get to see the, what do you say, solution. Okay, so yeah, that may happen. So I don't want to waste the time in calculating the same thing over and over again. We have done this many times. So this time what it will be different, I will have break-in points because I will have 2 zeros. So if there are poles, they will be breakaway, but as I have 2 zeros, so like root locus will come in here, right? break in and then go towards the real axis, right? So yeah, the fourth step is break-in point, which is the homework for you. Okay, which is the homework for you, right? So the break-in point will lie somewhere around near about here only, right? Near about this point only. Okay, this will come like this one. Okay, and then they will diverge. Okay, first they will converge, then they will diverge. Okay, also find the value of k, like is break-in point, and also find the value of k, right? What is the value of k itself? Okay, so yeah, these two you have to find out. Now let's find the angle of departure. So that is also and homework for you, right? That is also an homework for you. Okay, because like basic intuition, I will give how the root locus will look. So root locus will look something like this. Both of them will come over here and they will break away like this, right? But like this angle of fifth step, these are just calculations. Okay, I've calculated two of the one of those actually. Okay, now what will be here? Here there will be angle of departure, right? As I have two poles, right? As I have two poles, so there will be angle of departure here, right? Instead of angle of arrival. Okay, so what I will do is not give this one as homework, because this is just a new concept. So I will solve this one. Okay, I will solve this one. So because like at least I should solve two of them, then other things you do by yourself. If you don't do it by yourself, right, there is no nothing will be good for it, right? Because like if you just keep watching me that I am solving, it is not good. Trust me, it is not good. You have to solve it by yourself, right? So let's like just I'm giving this one because the angle of arrival and departure is same, like bit new. So angle of this time I will have angle of departure, right? Angle of departure. So again I will copy this one. Okay, here there is some difference, that's why I wanted to calculate this one. So what do I see is that I have to like I am calculating angle of departure. So what is theta d? Theta d is with respect to poles, right? Poles. So this time this will be 180 minus theta p and plus theta z. Theta p will get subtracted, right? Theta p will get subtracted. Okay, so yeah, that is this one. And so what are my angles, right? What are my angles? So my angles, I'm calculating this one for this p1, right? So let me name this as p1, p2 and z. Okay, so firstly I'm calculating for this with respect to this z, okay, along the x-axis. Okay, so this is, let's say, theta z, right? Next up I'm calculating with respect to this p2, right? So this is p2, this is, let's say, theta p2. I have only two poles and 0, right? So yeah, that is done. Okay, so now basically what we do is basically you find the theta z. Theta p2 you already know, this is like no x-axis distance and y-axis is 2, so it will be what, 90 degrees, right? So theta p2 I from figure itself I can see that it will be $90 degrees, right? Theta p2 will be 90 degrees. Sorry, it will be 90 degrees only. Okay, so now what will be my theta zb? Okay, what will be my theta zb? So theta z, right? Theta z will be simply what is the distance from this point? The distance is 5, right? The distance is 5. Now what is the distance of this point? The distance is 1. So I will write this one down. So this distance is 5 and this distance is 1. Okay, so both of the distances are 1 and 5, right? So now so what is happening here is I am going backwards 5. So this is my axis basically. So this is lying on the what quadrant? What quadrant is this lying? This is lying on the second quadrant. This is lying on the second quadrant, right? So yeah, if this is lying on the second quadrant, so what will be my angle be? Angle equation. What will my angle equation be? So theta z equals to 180 plus theta, right? 180 plus theta, you know that. Okay, sorry, not 180 minus theta basically. So I will go here and I will subtract this theta. This is the theta, right? This is the theta that I will subtract to get this angle. This is 180 and this theta I will subtract, right? So this I have already taught you, right? Very well. So I hope you remember. That's why I wanted to take this question. This is tan inverse y over x. Y is 1 and x is 5. So like what is tan inverse y over x? Like it is somewhere around 11 point something. So the value comes out to be something around 168.7 degrees. Okay, the value comes out something to be around 168.7 degrees, right? So now if you just put that these two values in the equation here, right, in the angle of departure formula, what do you get? So theta d equals to 180 minus 168.7 degrees plus 90 degrees. Okay, so what is this? So this if I write this, add this all up, so I am adding this to becomes 270 and this becomes minus 168, so this becomes, okay, I'm adding, okay, sorry for what I am doing, no, I should add 168 and subtract 190. I'm like in some other place, right? Sorry for that. So I have to add, so if I subtract 90 from this one, I have to add like this is 58, I have to add, so this becomes 238, right? So still I will, okay, still 90, yeah, this becomes 258 basically, 258 this becomes, right? So still I will just for confirmation 180 168.7 90, okay, yeah, 258 258.7 degrees this becomes, right? 258.7 degrees this becomes my theta angle of departure, right? So but what we know is, will it cross my j omega axis, so crossover point. So here also this is interesting. So angle of departure we have got, right? So will it cross my crossover point, like j imaginary axis, right? Crossover point. So for crossover point, what we used to do was s was equals to, we put s equals to j omega, right? We put s equals to j omega. So if you put s equals to j omega, what do you get? So basically it is 1 plus, like what is my equation? So equation is something like this. So I can directly copy this equation, okay, yeah, I can directly copy this one, right? Copy this one. So it is let me actually color this one, else it will go dull bit. Put j, so this, okay, I will not directly write it, j omega square plus 2 j omega plus 2 plus, okay, I have to take in common the k terms actually, sorry for this one, not the k terms, the s terms I have to take in together. So I will just copy this equation only, why we just understand, okay? So this one what I can write, yeah, s j omega square plus j omega 2 plus k plus 2 minus 4k should be equals to 0. Okay, now what is happening is that firstly we'll solve this one, okay, then I will go to this one, right? If I solve this one, obviously the imaginary component should be 0, right? Imaginary component should be 0. Now if the imaginary component is 0, either this can go to 0 or this can go to 0. Okay, in general what we used to do was, we rejected the solution omega equals to 0, but here we have to, why? Because what we see, it is crossing the at s equals to 0, right? It is crossing, because what is my range, what is my test point range? It is minus infinity to 4. So between this obviously 0 comes up, right? So 0 will be here, so omega equals to 0 is a solution, okay, as s lies between minus infinity to 4, hence omega equals to 0 is a valid solution. Okay, is a valid solution. And this is minus, so omega 0 is a solution, so like hence j omega 2 plus k equals to 0. By this we can infer that omega equals to 0. And what is the next solution that we will get? Next solution is putting the real components equal to 0. So here I will write the imaginary, I should write imaginary of 1 plus g of s into h of s equals to 0. Now I will equate the real, right? Real of 1 plus g of s into h of s equals to 0. So my real of 1 plus g of s into h of s equals to 0. So what do I see? So this is basically, okay, minus omega square, which doesn't matter because it is 0 anyways, plus 2 minus 4k equals to 0. So my k, like this is 0 anyways, right? This is 0. So k equals to 1 by 2. So k is 0.5. So k valid value of k. So k is 0.5, right? So I have already drawn it down here, right, and written few things. So k is 0.5. So I have also calculated the value of k and also the breakaway point. Okay, so it's not a homework anymore, but you try to solve it, right? And you will cross verify. If there is some calculation mistake, we can fix it, right? So yeah, k is this. Okay, from k equals to 0 it is starting, and at k equals to infinity it is terminating, right? K equals to infinity it is terminating. Okay, so yeah, like this we can do our root locus diagram for this particular gs into h of s, which was not in this format, but we converted this into a standard format to solve it, right? Always if some other format is given, convert it to your standard format. Okay, this is my standard format, right? So yeah, this is in the MATLAB basically. Okay, from MATLAB also you can cross verify, right? So like in different ranges I have given where the system is stable, unstable, all those things I have already given, right? I don't want to further extend. Okay, you just check it out for yourself and pause the video so you can understand where it is over damped, where it is critical damped. So these things are used in a controller chapter. Okay, because by this k parameter will be different in there. Okay, and from varying that from this table, right, I can literally understand where do I need to rotate the knob so that I want a underdamped system. So I will rotate the knob like this. The value of k should be in between this range. So if I want a critical damped system, exactly, I want to keep the value of k equals to 0.18. So it depends on where do I want to keep the controller. So that is known as the controller basically, and we will learn this in the last chapter, right? Last chapter. So yeah, root locus does help us to visualize and see at a glance what should be the values of k to get to a particular performance. Okay, particular performance, particular stability, particular characteristics I want, all those things I can change just by seeing the summary, right? Summary here. Okay, so yeah, now let's solve a gate question. So this is a gate question basically. So what I am thinking is I will give you this question in homework, and in the next lecture I will again solve this, right? Again the lecture will go on a bit long. So this is one of the question. So just take a screenshot and do this one. Okay, so very good question this is actually. So try to solve it, right? So this is also another gate question. Okay, try to solve it and we'll solve this in the next lecture. And this is like, this question is my added. Okay, this question is my added, so I have given the root locus for that one. So you can take a hint from here also. Okay, and yeah, this is a very good question. Okay, be very careful while solving this question. So take the screenshot and try to solve this question. Okay, so I think yeah, this is it. So one concept I wanted to explain, right, teach you, is that the effect of this is the root locus for that one. Okay, so effect of closed loop poles by adding by adding poles on the OLTF. So like I have already taught you the effect of zeros on my transfer function, but that was on the transfer function and that was on the CLTF. So previously what did I taught you is that effect of adding zeros on the transfer function, that is on the closed loop transfer function itself. But here it is different. So there whatever I told you, right, the effect, whatever the effects I told you, that was for the transfer function itself. For here I am not adding to the transfer function, I'm not adding to the closed loop transfer function. Here what I am doing, here I am adding to the OLTF. Okay, so these things you have to keep in mind. So you might be confused when I previously taught you that, right? So just revise and check your notes also on that lecture, that it was for the transfer function. And what is for the transfer function? Transfer function is for the CLTF basically. Here it is for the CLTF, right? And I am not adding poles to CLTF here, I am adding poles to OLTF and checking what does it do to my CLTF. Okay, that is very interesting. So if adding poles to my OLTF, what changes does it do to my CLTF? That is what I am understanding here. Okay, so just a warning that not adding poles to my CLTF. Okay, just keep this in mind. Okay, keep this in mind. So yeah, so these effects, right, these effects if you understand here, this will help us in controller chapter. Okay, to understand the why does this happen. Okay, this in control chapter this is very helpful. So what this point is telling us is that by shifting poles to the open loop transfer function, by adding poles to the open loop transfer function, has the effect of shifting the root locus to the right of the S-plane. Okay, just let me check if the English is correct. The root locus shifts to the right half of the S-plane, so I need to change this one. The root locus shifts to the, yeah. So by adding poles to the OLTF, basically I'm adding poles to the OLTF, right? OLTF, not the CLTF. Adding poles to the OLTF, the root locus shifts to the right of the S-plane. Okay, right of the S-plane. So it shifts, right? If I add some poles, right, I add some S+2 or like this another poles, it will shift to the right of this plane. We will see. I have plotted the MATLAB of those things, so you will see. Or if you can plot the root locus by yourself and you will check, right? They are shifting to the right. Okay, we'll just cross verify. Now, what does this mean? If my system, like the poles, like if my system root locus is moving more towards right, what does this mean? Let's say at initially, yeah, I have like this one, right? Like this one. All my poles are lying on the left hand side of the S-plane. Now I added a pole, and here no changes happening. Still they are on the left hand side of the S-plane, but it slowly moves to the right. Okay, slowly moves to the right. At the first stage, it was going towards negative infinity. Here, it's not in the negative infinity anymore. It is bounded here, right? Like a CLTF, closed loop poles. Now, if I further add a pole, what happens? Further add a pole, this goes to the right hand side of my j omega axis. So this makes my system unstable for few values of case. Here for all values of k, system will always be stable. Here for all values of k, system will always be stable. But here, right, for few values of k, system may become unstable. So that is a problem actually. That is a problem. So if you keep on adding poles in our OLTF, this might make our system unstable for few values of k. So not for all values, but for few values of k, this might make my system unstable. Okay, so it is very important to understand. Okay, now this means it makes my system less stable, right? It makes the system less stable. Now here, right, what it is telling, my response becomes slower. Why does my response become slower? Here, right, what I am saying is I have only one pole, so it is fine. Only one pole I have, like it is I'm not comparing it, right? So here what is happening is that due to this dominant pole effect, what is happening, this pole will be dominant and this pole will be not dominant. So what will happen, my what do you say, this distance will reduce. Okay, hence my time constant will increase, right? So you get it. So what is my time constant? Time constant is the negative inverse of my reciprocal of the real root. So reciprocal, like this is reduced, right? Earlier my pole was here, okay, only single pole was here, let's say, but here I have two poles and this will be more dominant. This will be more dominant, hence this distance has reduced. So reciprocal of this will be increased, hence time constant will be increased, hence my response will be slower. This all I have already taught you, right? All these things I have already taught you. Response is slower, dominant pole, there I have taught you with examples, all those things. So I hope you can recall this. So you have to, if you aren't able to recall, you have to revise again. So keep on revising, right? Whatever you taught. So we learned a lot of things. We learned a lot of things. So you have to keep on revising and do the questions. Okay, just by learning is not enough. You have to do the questions and apply to whatever you learn, right? Apply in the numericals as well. Okay, it's very important. Else you will just forget them. Okay, very important to learn all these things. Okay, so yeah, this is what you do. Okay, so yeah, here I can see my response becomes slower. Here my response becomes further slow. Okay, so just you have to understand with intuition, my response becomes further slower. Okay, because this is going more towards right. Okay, as it goes more towards right, my response becomes more slower. Okay, so because this one is the dominant one. Okay, so yeah, now that was for the effect of poles, right? Now what is the effect for zeros? So effect of closed loop poles by adding zeros to the OLTF. So what is the effect? By adding zeros to the OLTF, open transfer function, the root locus basically shifts to the left. Okay, I have to again improve the English. The root locus, just cut this one. The root locus shifts to the left of the system, right? So it shifts to the left of the system. Now what does this mean? this means it obviously makes the system stable, right? If initially it was going right, now I'm trying to push it back towards left, right? So whatever roots are there in the left of the j omega plane, then it will make the system stable. It will just do the opposite effect. It will make the system stable, but response become faster. But this is conditional, right? Conditional. Okay, why? Let's see. So I have this transfer function, this last one, right? By adding poles I got to here. Okay, by adding 2 poles I got to here. Now I want to increase the stability. If I want to add to 0, what will happen? So if I add a 0, what will happen? This is the previous case where I had 3 poles, right? And no zeros I have. Now if I add a pole, what do I see? That for all values okay, my system becomes stable. For all values okay, my system becomes stable, right? But the faster response, right, becomes faster response. It depends, right? It depends, because in the 2 pole case also we had similar type of response only. So it depends. Okay, it is conditional statement, because like it depends on the location of the poles and all those things. So that you can ignore. In the controller chapter, right, we'll understand this more in a better manner. But to give you a brief overview, an idea, like in controller this is what we do, okay, sometimes. So you will understand this. So you might ask, then sir, like if this is giving me faster response, also this is making a system more stable, so we will always add zeros, sir. Why will you add poles? So adding poles has obviously its advantages, right? So obviously if you get some, you lose some, right? So there is always that case. So you have to have a proper balance. So we'll see why we want to add poles now. Like adding zeros, you are seeing beneficial. It is making my system stable, and also it is like reducing the time, right? It is basically making the response faster. So what is the problem? We'll see, right? So yeah, I hope you got the basic overview and intuition of this, right? So just wanted to give you a brief overview. So in the next lecture I will solve those questions, and I will give you the answer to the homework questions or something. Okay, I will just put it in the notes and you check the notes, right? So yeah, I think that's it for this video, and thank you for watching. I will see you in the next lecture.